In this question, we have to work out the value of x and the value of y, and we need to give our answers to two decimal places. We're first of all given the area of the triangle ABC. It's telling us it's 14 centimetres squared. So if we use the formula half AB sine C, so that's the formula for area of a triangle, and we need two adjacent sides, so we have x and we have 5, and we need the angle between them, and we've got the 120. So what we can write down is that half times x times 5 times sine 120 must be equal to 14, 14 being the area of the triangle. Now you could simplify this on your calculator. You could work out a half times 5 times sine 120. However, we're going to approach this assuming that you need to work out sine 120 without a calculator, as that is actually something you need to know anyway. So we're going to practice that now. So let's leave this question for a moment. 120 without a calculator. Now there are certain angles that's useful to know. I would say 30, 60 and 45 would be three of them. So if we consider an equilateral triangle, then all the angles would be 60 degrees. If we split an equilateral triangle in half, then what you have then is two right angle triangles. If I say that one side of an equilateral triangle is 2 units, say, then this side would also be 2 units and the other side would be 2 units, but if it's split up in half, we could say that this line would be 1 unit, as would the other line. If I just draw this right angle triangle again down here, then this is the information that we've just worked out. If we have the interior angles of a triangle being 90, 60 degrees, then the third angle would be 30 degrees, as angles in a triangle add up to 180. The missing side, we could use Pythagoras to help work this out. We would know that the hypotenuse is 2 units, the other side is 1 unit, therefore the missing side would be the square root of 2 squared minus 1 squared, which is the square root of 3. So any equilateral triangle will follow this pattern. You would have the 60 degrees, 30 degrees and 90 degrees as the interior angles of half an equilateral triangle. And then if you look at the ratio of the sides, then they would always follow that you would have the 2, the 1 and the root 3. This triangle is worth learning because it does now enable you to work out the exact values for sine, cos and tan of 60 degrees and 30 degrees. If we first of all remember the ratios of sine, cos and tan, sine of an angle, and we'll use theta to represent the angle, so sine theta is equal to the opposite side over the hypotenuse side. Cos of theta would be equal to the adjacent side over hypotenuse, and the tan of the angle, tan theta, would be opposite over adjacent. Some people like to remember this as SOHCAHTOA, as a way of remembering the ratios for our trig functions. If we look at 60 degrees, sine of 60 would be the opposite side over hypotenuse, so root 3 over 2. So that's an exact value for sine 60. And in the same way, we can work out that cos 60 is 1 over 2, and tan 60 is root 3 over 1, which would be the same as root 3. We can also do the same thing for 30 degrees. If we have a look, then sine 30 would be 1 over 2. Cos of 30 would be root 3 over 2, and tan of 30 would be 1 over root 3. So those are the exact values for 30 and 60 degrees for our trig functions, sine, cos and tan. Now remember, the exam question though did ask for sine of 120. So what is the connection with these angles? First of all, consider the graph of sine x. Then if we have a look, we do know that sine of 60 is root 3 over 2. So if I label this on the graph, so 60 degrees would be about here. And if I draw a line going straight across, we can see that there's another value of x that would give the same value for y as 60 degrees. We have it here. Now we can use the symmetry in this graph to work out that if this gap here is 60 degrees, then this gap would also be 60 degrees, which would mean if I do 180 and work back 60 degrees, I would know that that's 120. So I can see from this graph that if sine of 60 is root 3 over 2, then that means that sine of 120 must also be root 3 over 2. So sine 120 is root 3 over 2. Sine 120 is root 3 over 2. So I can substitute that value in. So I can now write down a half times x times 5 times root 3 over 2. I know that's equal to 14. We can simplify the left side. A half times 5 times root 3 over 2 would be 5 root 3 over 4. And we've got the x after it. So we know that's equal to 14. If I now multiply both sides by 4, that would leave us with 5 root 3x on the left side, and 14 times 4 is 56. If I divide by 5 root 3 on both sides, it would leave us with x on the left side and 56 over 5 root 3 on the right side. And if I type that in on my calculator, as the question did ask for our answer to 2 decimal places, I can see it's 6.46632, which would be 6.47 to 2 decimal places. So we have now worked out the value of x. The next part is to work out the value of y. So if we have a look at the triangle, we can see that we could use the cosine rule. Now the cosine rule is a squared is equal to b squared plus c squared minus 2bc cos a. If we say that a represents the side we want to work out, so in this case y, then b and c would be the other two sides. And cos a, that's a, means the angle opposite the side we want to work out. So we're going to write down that y squared is equal to 5 squared plus our answer to x, so 6.47 squared minus 2 times 5 times 6.47 times cos 120. Now you can literally type all that in on your calculator in one go, and we can then work out the square root to get the value for y, which would leave us with 9.96 centimetres to 2 decimal places. So we have the value of x and y. Now just as an extra note to be here, if we look at cos 120, again, I know you can type it in on your calculator, but just to look a bit more at this by considering without a calculator, let's consider what the graph of cos x would look like. I just want to emphasise that if sine of 60 is root 3 over 2, then sine 120 was root 3 over 2. That doesn't mean that cos of 60 and cos of 120 would also be the same. Because if you have a look at this graph, 60 degrees would be about here. If I draw a line going straight across, we can see actually that the other value that would give us the same value of y as 60 is not going to be 120 because it's over here. We can still use the symmetry of the graph to help us work out what this one would be. That gap is 60, which means this gap here is 60. If I go through 60 and work back 60 degrees, then that value would be 300. So actually, cos of 60 is a half, then cos of 300 is also equal to a half. So that means that cos of 120 is not the same. If you did want to know cos of 120 from this graph, if you have a look where it would be, roughly here, then actually you can see that if cos of 60 is equal to a half, then actually cos of 120 would be minus that. So cos of 120 would be minus a half. So it's worth learning the triangle, equilateral triangle that can be split in half to get your values of 30 and 60, because there is something you need to know. And it's worth then considering what the graphs of sine, cos and tan look like to help you work out other values that give you the same answer.
This question uses the formula for the area of a triangle and the cosine rule. So you've probably seen it before, GCSE maybe, but I wonder if you could now prove the formula for the area of a triangle, cosine rule, and indeed the sine rule. So let's have a quick look at that. For the area of a triangle, it's relatively straightforward. So if we draw a triangle, we call this angle C, so that's side C, and then pop the other sides in. Now, to get the area of a triangle without involving an angle, we know that's the half times the base times the height, and that's the perpendicular height. So that would be that side there. Now we also know from the triangle on the left hand side now of the main triangle that the sine of angle C is the opposite, h over the hypotenuse A, which means that h is equal to A sine C, and then our area becomes a half B A sine C, and then to make it alphabetical we call it AB sine C. So that's the area of a triangle. For the sine rule, again, we'll draw a general triangle, and ABC, ABC, and again we're going to drop a perpendicular down, so that's H, and then we can see we've got two smaller triangles within. So for the first triangle we have that sine of A equals H over C, and for the second triangle we have sine of C equals H, the opposite, over A, the hypotenuse. Now the first one gives us H equals C sine A, the second one gives us H equals A sine C, and therefore we can put those H's equal to each other, so that gives us A sine C equals C sine A, and therefore A over sine A equals C over sine C. By the symmetry of the situation we can also conclude, we'd use a different perpendicular drop down, but we can conclude that that also equals B over sine B. Important to remember as well that all of these, if we invert them all, they're still all equal, and so sometimes it's quicker and removes the possibility of a little slip in calculation to start with the sine on top. Now for the cosine rule, a little bit more complicated, but let's draw ourselves a general triangle, and we have angle A, B, C, so that's A, B and C. And again we're going to drop down this vertical, so call that H, and what we're going to do is we're going to introduce another variable. By the way, there are plenty of other ways to prove this, but I'm going to do it this way. So from the corner C to where the H drops down is X, which means that the other portion is A minus X. Okay, now the next thing we do is we apply Pythagoras. So if we look at the left-hand triangle, so I'll label those triangles again. So for T1 we have that B squared equals H squared plus X squared. And for triangle 2, we have C squared equals H squared plus A minus X squared. Okay, so now we can subtract those two equations to get rid of h. So we have b squared minus c squared equals x squared minus a minus x squared. Now the right hand side we can then multiply the square out, and then we see that the x squareds cancel and we're left with 2ax minus a squared. Okay, now we can rearrange all of this, which I'm going to do in one step, to give us c squared equals a squared plus b squared minus 2ax. Now, if we look at the length x within the triangle T1, so we're again looking at T1, then we see that x is the adjacent to the angle, and that means that we have cos of c equals x over b, and therefore x equals b cos c. So if we now substitute that back into the equation we reached at the top of this side of the page, we get c squared equals a squared plus b squared minus 2ab cos c. And obviously we could, well, I say obviously, with a bit of thought we can see that we can rotate the a, b and c because they're arbitrarily named on the triangle, so that will give us a squared equals b squared plus c squared minus 2bc cos a, and b squared equals c squared plus a squared minus 2ca cos b. So, little quick addition to the cosine rule, which I'm going to show you on GeoGebra because it's fun. So, here's the formula, that's with the numbers in, and there's the calculation. Now, what happens if we move this point along? Well, the angle changes, so the cosine changes, and so the formula changes, but then when we get to here, something interesting happens. We've got nothing there because we've got the cos of 90, and so if we get rid of the blue writing we can see that we're into a Pythagoras. So what that means is we can think of Pythagoras as a special case of the cosine rule. And there you go, that's the proofs of those three. Hopefully you had a go at trying to remember them beforehand, or if you have never seen them before, you could work through them line by line and see how it all works. And I think that's all very lovely, as I may have said in previous videos about other